My name is Suchánek. I'm coming from the company called Baremon, and today's presentation will be about analytical functions in PostgreSQL, which might be in some cases a very good alternative to aggregate functions. So let's move on. This is something about me. I started working in IT in the middle of 90s. Especially when I started what is related to this topic. I started as an ETL developer in 1998, dealing with a large platform, dealing with a large set of data, creating data warehouses and the reporting tools and such information needed for financial, for online analytical processing and such information. So why did the SQL love window functions? Because window functions is just another name for the analytical functions. Because they always get things in order while they stay partition. Might be some kind of nerd joke, but we will deep dive into the meaning of that sentence. And you can see that maybe if you are familiar with SQL, that analytical functions bring some kind of disorder and chaos into the thing, but at the end of the day, everything is in order, even if it's partitioned and a little bit in chaos. So today's agenda, we will briefly introduce what is analytical functions, what their purpose, what is the history of the analytical functions, who was the first platform introducing them, what is the purpose of analytical functions as well, why analytical functions, even they are more than 20 years old, but they are still underutilized. Then we will deep dive into a little bit in the theoretical introduction to the analytical functions, what they consist of, what they are parts, what objects we can met when dealing with analytical functions, and then when you can replace some aggregate functions with analytical ones, where you cannot, obviously. And then we will deep dive into practical examples of the query optimization, for example, how to rewrite some functions which is using all known aggregates with another approach using the analytical window functions, and we will go through different examples which might be useful. So what are the analytical functions? It's not a rocket science. Analytical functions, they just provide some enhanced capabilities for performing complex operation, such as rankings, cumulative totals, cumulative averages, moving averages, and other advanced calculation across a defined set of rows within a data set. Unlike aggregate functions, which are completely fine, but they just summarize data and they return a single result for a group of rows, for example, the sum, average, maximum, minimum. And analytical functions, they retain the row level granularity, while simultaneously they calculating the values you need based on the defined window that we will explain later on, or a subset of the data based on some criteria. This allows us to do more dynamic analysis, especially in ETL and reporting field, that enable us to do comparisons, some trends, and insight to the derive without losing the individual record and row details. These functions are particularly useful in the scenario like financial reporting, performance tracking, salaries, whatever, or any context when you need to understand data trends or relationships across a subset of the data. And it is crucial. By leveraging the over clause that we will explain later on, analytical functions enable partitioning and ordering of data to suit a wide range of analytical needs, making them individual and valuable in modern SQL data analysis. So let's move on. Why they are important, the analytical functions? You can live without any issue for the whole life without using analytical functions, because if you are developing or maintaining some OLTP application, when you just deal with simple records, 1, 2, and you are doing just some transaction processing, you don't need them at all. But if you are dealing with some kind of data warehouse, when your end customer, for example, some LOB in or financial or risk management, they ask you to do some segmentation, to trend analysis, or whatever, you have two choices. You can still use some aggregate functions. You need to perform some operation over and over again, or you can develop this functionality in a third-party tool, like you can write the functionality in Python, in Java, whatever. But the key information here is that there is something which is already available for ages, more than 20 years. And this is analytical function that is a part or core part of your SQL engine. So they are highly beneficial because they allow you to access a table or data set only once, to perform multiple calculations. And it is reducing the overhead of communication between the client, that might be some application server, reporting tool, and on the other hand, there is a SQL server. Instead of sending multiple requests and round trips between the client and server, you just execute one single query and the data set is being returned without any issue. You can use this, as I said, for analytical functions, for rankings, running totals, averages, moving windows, whatever. And this approach not only minimizes the network traffic, but also it significantly improves the performance, because once you access the table only once, for example, you need in a table to go over all rows, and for some of them you need to calculate and deal with, for example, department average salary or some cumulative year-to-date sale sum or something like that. And if you access this table only once, because this information is already known to SQL server, then you save the resources, for sure. And also, SQL servers are already optimized to do such operation in memory, and rather than writing your own code, for example, in Java, whatever, or Scala, then you have a tool which is already available for free, because you don't need to pay for the analytical functions options. That's just a core part of your SQL engine. And for sure, by offloading the computation to the SQL server, you can take advantage of the efficient architecture of the SQL server, and you save the processing power, and it's resulting in the quicker response and more streamlined data analysis. Some brief of history of analytical functions. They have been introduced in Oracle 8i in 1999. At that time, I was nearly joining the Oracle company, but they became the standard in 1999, which is known as SQL3. So it was Oracle that pioneered this analytical functions that was a part of online analytical processing part of the SQL server. And over the time, the major database systems such as Postgres or SQL Server, MySQL, even nowadays you have that in memory or small databases like DuckDB, they also support analytical functions for the purposes. So really, the history is long. And what is interesting here, the PostgreSQL milestone that first version, when Postgres adopted analytical functions, that was 8.4 version in 2009. There was some initial support for windowing functions, another name for analytical functions. And it was some enhanced functionality, some ranking functions. They introduced some row number, rank, dance rank, entile, and for sure the analytical part of the aggregate functions like sum, average, minimum, maximum, and count over a data set. Just to sum up, what is the purpose of the analytical functions? Nothing more than save resources, enhance and optimize the performance of your SQL query, and it allows you to avoid some post calculations when you need to find out the information for individual rows while keeping the detail of your SQL query. So nothing really interesting. What are the key use cases? And so you can use for ranking. So you have the functions like rank dance, rank, row number. Comparing by offset. You can, in your database, for example, if you have a row, you have the possibility to access the previous row, or nth previous row, or nth, some neighbor elements, or following rows. You have some kind of boundaries. So you can, for example, compare the previous record with the current row, and based on that operation, you can also calculate something which might be needed by the client. So also you can do some aggregation, some rolling aggregates, for example, some year-to-date sales sum, etc., etc. And now we are moving to the core syntax. This is not the SQL standard, but because we are on Postgres conference, this is something which is very cool, and it's just relating to the Postgres. You just perform a simple query, select column 1, column 2, column 3, then you can call some window function over 1 column or 2 columns, over, and then you have the window. And Postgres syntax allows you to define the window function just after mentioning the table you are selecting from, and you define your window. So your window is here, for example, partition by some column 2, order by column 1. Why it is very handy? Because it's more readable than defining the window function in the select list. And for sure, that window is just an alias, and you can reuse the multiple columns when selecting data. You will see that later. Why they are underutilized? Well, Even myself, I don't remember teaching MinDest on university. Most likely because it was not available at the moment. Because I'm not that young. But analytical functions are often underutilized because many developers and analysts are unfamiliar for different reasons with their capabilities, and or they find the syntax a little bit intimidating because it often resembles formulas and functions in Microsoft Excel, which every developer instinctively despises. Another reason for that students typically do not encounter analytic functions during their studies. It's understandable because we are assuming that it's just a skill and to be picked up only when you are working on that field. Anyway, developers may default to writing some complex queries, join whatever, with third-party languages or using all aggregate functions, and now we will just explore the ways how we can improve that. So our goal today would be to go through some practical examples, and later on we will run some queries on a virtual machine and to show what is the difference in the code, how it can be rewritten. So basically, any of SQL engine is optimized for window function, because if you are trying to develop something on your own, it might work without any issue. But usually, SQL engines are developed by many developers with a lot of experience. Usually, they are able to come up with better solution for your analytic purposes. And also, when you do some proper indexing on the columns, then you can benefit from the architecture of the SQL server. So, key components we have in the analytical function. As I told before, we have something like which is called window. That defines a data set we are working with. The window can be the entire table we are selecting from, or you can partition that window by the clause partition by. Just imagine that this is a window, and like old Windows was not big like that. It's into part, but the partitions are nothing more than a small parts of that window. And SQL engine can work in parallel with all the partitions in the same time, with it based on the criteria. Then we have the partition, or the window can be, for example, just imagine that you have the result query and you have order by whatever. By 1, 2, 3 column. But when working with the partitions or windows, they can be accessed with different ordering. And when you are returning the result query, that order by is applied to the result which is given by the SQL server. But when analyzing and doing the analysis, the order by clause, it defines just the sorting within the partition or within the window. Then we have frames. And especially I found the frames very, the part which is causing the underutilization of the analytical functions, because That's something which is not easy to understand on the first sight, and one must be more familiar with that. I will explain it right away. We have some kind of ranking functions. We can use. We have some offset functions which can access the previous row within the partition or within the frame. We have also some aggregation functions we can use for analytic purposes, and we have some statistic functions for percentile rank, for cumulative distribution. And so let's deep dive into frame, because that is something which is really, really unique. Let me. Okay. So, what is the frame? Just imagine that you have a select, you are going through the records, and every single time, the SQL engine, which, for example, is working with the row with Henry, which has this salary, for example, you have something like frame, which is a moving window. It can be a partition, can be even the entire table, but it can be a small subset of it. And you are able to work with the frame start, and you are able to work with frame end. Those are things that you can define in your SQL query, and those things may vary based on the analytic function which we are working with. It means that every single function which can be used as analytical, it doesn't need necessarily work with frames. You need to go to the documentation and read carefully what it is working with. For example, if you are using the analytical functions lack and lead, and you are working with the Henry row, that lack 1, you are the access to the grace. When working with lead, is the following one. If you change the lead 2, it will work with Frank. If you change the lack 2, it will work with Emma. If you are exceeding the offset of the frame, it will return null. You need to deal with that. For example, here we have the first value, last value, and end value. This behavior is the same. Working with the frame. Maybe I will go back to the presentation, just a little bit of theory on that. In some functions, you have something like default frame. Default frame is the range between the frame start, which is the start of the partition, and the current row you are working with. It allows you to easily do some cumulative sums, for example, year to date. But this is default frame. It looks like it might be default for every single analytical functions, but that is not true. And there is a good practice to always mention that default frame for the readability purposes and for the migration purposes. For example, if you are, migrating from one platform to the another, that, for example, Oracle might have a different framing. I mean, the default one, that Postgres, it can be different from DB2, it might be different from another platform, or even when you are migrating from one major release to the other one, you may also encounter some changes in the default behavior. So like in other programming languages, if you are working with something which is assumed to be default, it's a good practice to write down, because explicit is better than implicit. As I said, the frames are supported only by some functions, usually the offset that are working with previous and following rows, all the aggregate functions, and for other functions, frame equals to the partition, and we will see the partition definition in SQL. We have also different frame types. You can work with previous row, but that's for unique row. But also you can work with groups of records with the same ordering type. For example, if you are working with some department and your partition or frame is defined by the department, that you can expect that you have multiple records for the or people working in the same department. So you can work not only with the rows, I mean the individual people in the department, but you can also work with the entire group. And we have also a range frame type, which is working usually with numeric data types and data types. It's for range operation. As I say, usually when you have the frame boundaries, that you have unbounded preceding, so that means the start of the partition. Then you can define the n preceding record. You have the current row, you have n following, and then you have the end of the partition, I mean unbounded following. Those are keywords that you can use in your SQL query. Just to show you what are the, for example, unbounded preceding and following here when we are working with rows, groups, or range. For example, we are working with Mandy row. So unbounded preceding is the start of the frame. So in this case, it's James. Unbounded following means Phil. And it applies to all, I mean, regardless the definition of the frame, when you are working with rows, groups, or range, it remains the same. What is different? Because the keyword current row is common to the rows, groups, and range frames, but every time it means something different. Current row, when we are working with the frame defined by the row, is just one single row. In this case, it's Mandy. When we are with the group, because the frame is defined as a group, that we have two records, we have Mandy and Jack, and for range, it is the same as for the group. And for example, and preceding and following, for example, when we are looking for two following, then when working with Tom, that our range is from Tom to Jack. When we are working with groups and the frame ends to following, that we are working with 4 records, whereas if we have a range and working with 15 following, I mean we are working with the salary information that 84 plus 15, it ends up in 106. So we are working with that range. It might be interesting. We have also some kind of operation or SQL syntax that allows to exclude something. You can exclude current row, you can exclude the group you are working with, and or you can exclude ties. So it means the current record, but exclude equal to it. Or you can filter. So we will work with that. When to replace the aggregate function with the analytical 1. Usually, when we are working with the entire table, and we are not interested into aggregates or average or something like that, but we want to keep the row level detail and add some information. So, for example, what is my, how to calculate, for example, this, what is the difference between department average salary and my salary? You can use aggregate function to find it without any issue because you can create a subquery which finds you the average salary for the department. Then you have access to the same table the second time. I mean the entire table, not just for the aggregation. You get your own salary. You just perform the math operation. You got the difference. But you need to access this table twice. Or you can use analytical functions. You can define the window by partition by the department. You can get the average salary in the department. And within one single access, you can get the average of the department salary comparing to your salary, and you have the difference. That's just the use case. And to be honest, nowadays it's very easy when you are unsure and, for example, you have a very complex query and you can see that you have, for example, some common table expression there used in your query later on 15 times for different types of aggregation. Just use ChatGPT, Claude, or Copilot. No issue with that. They are trained well and they will give you very interesting results. Whether it is worth to use analytical functions or the old approach is still valuable, which might be completely fine when we are working just with a couple of records or 100, 1000 of records in your table. This is completely fine. You don't need to overwrite it. But if you are dealing with milliards, billions of records in a table, that every single improvement in the query that counts. So just the limitation of the aggregate functions, they collapse rows, so you don't have the access to the details, and you cannot combine summary and detailed data. That's all. That's why we have the access to the analytical functions. And now we can go to the details. I have some schema which is just using the employees and salaries table. So, for example, we have, this is visible, I guess, or do I need to make it larger? Larger, okay. I see window, editor, zoom in, zoom out. The other one. More? Or enough? More. So, for example, here we have a SQL query, which is using some kind of count. This is not a replacement by aggregate functions, just mentioning that count. It's not a really good example, but just showing that when we are performing count over a table, it needs to calculate the exact number of the counts. Whereas if you can use exists, it's more efficient because both queries will return department. They have at least one employee with a salary over 100. But the exists version is generally more efficient because it just stops searching once they one SQL found a salary, and it just lists you departments where departments having employees with a salary over 100. So it's not an example of analytical functions, but still, when dealing with some queries, this is a never-ending story. It's usually written by junior developers. They are overusing count when the right way is the exists. But let's deep dive into analytical functions. For example, here we have department comparison. We are calculating my salary or people's salary and difference with average salary of the department. So, for example, you can easily calculate it as written as an inline query, or you can use it even in a join. Better, you can use as a common table expression, but still you have a possibility to use a windowing or analytical function. You just select the name, department, salary, then you have salary minus average salary over some windowing function that is defined later, and this is the difference from department average. And the default window is defined as a partition by department. So SQL engine already knows the department you are working with because the current row has the department column. In this case, the windowing partition equals to the frame, so it calculates the average, and that's fine. So I will run it on the server, and let's just compare what's the cost of that operation. So we can see the initial is 0, estimated 12.75. Not that bad because we don't have too many rows. But guess what? Anyone try to guess what will be the cost for the analytical function? We have 12 for the aggregate. 7. Now even less. $243. Still, you have the initial cost is every time a little bit higher with analytical functions, but estimated one is usually a smaller one. Still, the cost doesn't say everything about the performance of your query, but you can use it as a good starting point. Then we have another interesting function that we have. That was execute. We have some running total. For example, running total expenses by year. So, for example, we are calculating the sum of the expenses from the beginning of the year. And you have the fields like year and month, so it will be a running total. So let's calculate it the old way, which is completely fine. So cost is about 15. And now we have a windowing function doing the same. And you can see that it's a little bit more complicated. We have the year, month, expense, everything we are accessing as before, but we are calculating the sum of the expenses over the window. And the window is defined by partition by year. So we already know the month, we already know the year, so we partition by year and ordering by month, by ascending. And now, because we are calculating our running total, so we are defining our frame as a rows between unbounded, so the frame, this is the partition start, and the current row, because for every year, month, and expense, we are calculating the sum. So let's run it. You can see that cost is 10 times smaller, especially when using a large data sets and calculating the running average, running sum. This is a typical use case when you can really benefit from that operation. And when I execute the query itself, it's, you can see that it's by year, by month. You have amount of expenses by year and year-to-date expenses. This is a cumulative sum. So, for example, we can do some employee salary ranking within a city. So, we can use some inline view on the row level, or you can write it as a join. It doesn't matter, but still you are accessing the table twice. So the execution plan is as follows. As you can see, we are accessing the table twice with the cost of 12.77. When rewritten with ranking over some window, it's very easy that you define your window as a partition by city, because it's a rank over the city. Ordering by the salary on the descending manner. You run just the execution plan, and it's nearly 10 times faster, giving the same result. Then a typical example for financial reporting or whatever, it's a moving average of the value you are looking for. So you can write, for example, the year, month, expense, and you are looking for the average expense by the year, and you define that query as it is like that. So usually, by the way, that's not a really bad SQL. It's written when you have the indexes on the right columns. It's usually not that bad, but still you have a better way. Then you can see we are accessing the table twice with some cost of 1762. When rewritten with window, moving window, that you have you don't have the partition, you have only order by year, and you are accessing the rows between two preceding and the current row, so you have a running average, and you can see that it's more than 10 times faster, I mean from the cost perspective. And we can continue with other SQL queries when you can use them for to find a minimum. You can find it to maximum. You can work with previous. That would be, for example, you are looking for gaps or can find a percentile within the department using that, or you can month-over-month expense changes, and so on and so on. What I will also like to mention that in Postgres you can write your own analytical function in C, because there is C API which allows you to do that, and you just compile it the same way as an extension or another function. And when you mention the Windows API.h, you just write a function in C, you compile it as a shared library, you copy it, and then you create in SQL your function the same way. This is very unique because even in other databases you are not allowed to do that, but as Postgres is open source and you have the way how to add your own extension, that you have the C API which allows you to do that. So let's go back to our presentation. So what you can use as a very good resource, there is a book which has been published last year by Anton, and he's focused mainly on PostgreSQL, and he's explaining very well the differences between partition window and working data set. It costs about $25 or something like that. It's very useful. I was mentioning because it's very, very useful, and it has about 200 pages with very good theory behind that and very good examples. So here we have some contact to me, and I would like also to mention my colleague Barbara Linhartová, which is a co-author of the presentation, sitting somewhere like that. I think, yeah, we don't have too many women here. She's the one, maybe? No, my bad eyes. And we thank you for your time. And I hope that you will at least think about the usage of analytical functions when you encounter the query, when you are calculating some aggregates, accessing the table multiple times. You have better ways how to deal with that than programming the functionality in the third-party language. Thank you.
Okay. Thanks a lot for the talk. Are there some questions? We have about a minute for questions. Yeah.
Thank you very much. Just one question. Is there filtering possible within analytical functions?
Sorry, can you repeat that?
Is there filtering possible within analytical functions?
It's possible.
It is, yes. Okay, and can you show, please, a syntax or something?
Yeah, I can you attach to the presentation later on. I can show you the examples of the function.
Okay, thank you.
I will attach it to the presentation that will be downloadable from the website.
Tak jo, děkujeme za přednášku.